So the next topic is the next section is to use residue theorem to help evaluate uh, some infinite sum over integer function. Okay, and the explicit example here is this sum of the form like that. So if you have a sum of n minus infinity, f sub n is integer, obviously. Okay, and then to evaluate that, then we multiply f by a trigonometric function that actually for this case is first change n to z. We'll evaluate complex integral and then multiply by this function pi cotangent of pi times z. Okay, and then do a loop integral over a large circle. Okay, and so that you draw the circle here, the complexity plane, and you look at this integral. So cotangent is cosine divided by sine, right? So the denominator has a sine pi z. So sine pi z is 0 at integer z. So all the integer will give you 0. 0 of sine in the pole of the integral. Okay, and then the pole, all simple pole, because all the sign are just the multiplicity of 0 is just 1. So we have all the 0 of sine here, 0, 1 minus 1, because you multiply the pi to make it more convenient. It's all the 1, 2, 3, all the integer points are poles. You have all the poles are here, right? And there are more other poles due to the f. So whatever f is, there could be other poles somewhere. But the first case you consider is that all the poles of f are not on the real, not the integer. Okay, if that would be the case, I mean, there's example to talk about that, how you treat that. But there are the poles of f. These are poles of f, or wherever it is. Okay. So now you integrate this over a fixed circle with weight is r goes to infinity. But obviously, you don't want this path to hit any pole. So this path is, so basically this is not an integer. The radius is not an integer, so that you don't hit directly on the pole. So that is just for argument's sake. That doesn't matter because we are taking this to infinity. So that when you evaluate this path in this loop integral, you include all contribution from all poles. Obviously, there's still poles outside, but you're doing it at the limiting sense. So you're saying that taking r to infinity, then all the poles will cover all the n goes to infinity. So you just symbolically you can write it as an infinite series of the summing over the residue from this integer, the poles at the integer, plus the residue at the pole of f. Okay, so now use the residue theorem. That's 2 pi I and sum of the residues. So the first is the residue of this the whole thing at the residue of the 0 of sine, so at all the integer. So basically sum over all the integer. And now you can use the one of the result and one homework. When you remember the one homework question, if you have a ratio that there's a denominator that for cotangent, the pole at cotangent. Anyways, cotangent is cosine divided by sine, right? So basically, the residue is take a cosine at the location of residue divided by the derivative of sine at the residue. So that's the homework question. Have you done that one? Finished? Not even finished with that part. That's early, yeah. That's early. All right, so we use that to calculate the residue. So and obviously for the poles and assuming this it's not singular, FC is not singular, so you evaluate at the location of the residue at the pole, which is just C equals to N, and then the residue of this one is pi and cosine of n pi, and divided by the derivative of sine, which is also cosine of n pi, and then multiplied by pi because there's a pi. If you take a derivative, you get a pi out, right? And so you see that these all cancel, right? And then plus the sum of residue of f, residue of f pi cotangent, residue of the whole thing, but at the whole of f, right? So the poles of the cotangent here, the poles of f, the rest, okay? And then you see that the first term is just what we try to calculate, right? And so then the last argument is that we want this integral I infinity to goes to zero. Now we just argue that I infinity. So I infinity goes to zero because the property of the integral. So we need to argue that g fc, the argument of that, or the argument of the whole thing, goes to zero as z goes to infinity. So that's a restriction that imposed on the function f. Whatever you want to sum, you need to satisfy that. And then the rest is finite because a cotangent is cosine over sine, right? Yeah, cosine over sine. But then both cosine and sine, so you see that let's just write it for argument. Cotangent, whether you keep pi, doesn't matter. So this is cosine divided by sine, so it's e to the pi, e to the I pi z plus e to the minus I pi z of compact z, and then you have I. Doesn't matter. This for arguments it doesn't matter. Right. And for large z or large magnitude of z, then these exponential function, one will be exponentially large, the other will be exponentially small. So you can ignore the exponentially small one, but both have the same term. So if this is large, then this is also large. So the ratio becomes finite. If the ratio is one, right? If this is large, you can ignore that. This is large. The ratio is minus one minus I. But there's still finite. The ratio is the magnitude of this. The cotangent function at large distance is finite. So if this is satisfied, then I infinity will be zero at the limit of r goes to infinity. So this integral goes to zero. Arguing that this equals to zero. So then the final result, final formula that you can use is sum over n minus infinity to infinity f as a function n is equals to minus of, using that is the sum of all the poles of f. and then the residues of F I cotangent. Okay, so that would be the formula. Yeah, that's 11.122. It's okay. So yeah, that's how you get the formula. So to use it, whatever you want to sum over the a certain expression, you change it to a function as a function n, and then change n to a function of z, and multiply pi cotangent pi z, and sum over all the poles of f only, not include the cotangent, right? And then you can use this formula. It's okay. So that's for this kind of sum. There's another form of sum. You can do it the same way. We don't want to go through that again, but there's a table 11.2, and there are different forms. So the next one is you have alternate signs, so you have a -1 times n in here, and the convenient series to use instead of cotangent would be multiplied by cos or 1 over sine. Instead of cosine pi z over sine pi z becomes just 1 over cosine pi z, and that will alternate the residue. You see that the residue alternates the sign. That's just the property of the sine function. Okay, the location is still n pi, or still n, right? So that covers this alternate sign summation. So that's the next formula. Except that that formula has a typo on the table. I don't know whether your printed version has that. At least my book has the extra n at the end of the formula. You look at the second line on table 11.2. The summation one that there's a last n is a typo. Take that one out. Do you have that one? Yeah. Fn times n. That extra n is not there. Okay. So that's a typo. All right. And then you have the other two lines. The formula Fn plus 1/2. Since the Fn, so you can see that you can still use the Fn plus 1/2 is still a function n, but more conveniently, maybe instead of using cotangent, you use tangent. And likewise, the alternate sign of that use 1 over cosine. Okay, so let's look up the table. Whatever series you can fit the form of the summation, and then see what formula, what the function you want to use to do that. It's okay. So that's how you use this table. And the only subtlety for using this method is that sometimes the given series doesn't go to all the range. So it's like not always from negative infinity. Maybe start from 0 or start from 1. So that one complication. The other complication is maybe when you write it in this form, some of the poles of F actually are on the same location as this integer pole, and then you need to treat it separately. So those are the two complications for using it. So the two examples are covering this. We'll go through that quickly because